Over 1 million events a second for 100 enterprise clients. How do you get to that kind of size? Today we'll be hearing a scaling war story from Liz Fong-Jones of Honeycomb. But before we get there, Streaming Audio is brought to you by developer.confluent.io, the one place to learn everything you need to know about Kafka, whether you're getting started or, yes, trying to scale those performance issues. We'll give you all the information you need to know, and we'll also teach you how to use Kafka and take you through some step-by-step courses. If you want to use those and you sign up to Confluent Cloud, do use the code podcast100. It'll get you $100 of extra free credit so you can take that course a little slower or a little larger. But before then, please enjoy today's episode of Streaming Audio. Welcome to Streaming Audio. My guest today is Liz Fong-Jones, who is a developer advocate at Honeycomb.io. Has been for the past 3 years, is that right, Liz?
Just about coming up on 3 years in February.
Coming on 3 years. Right, so what are Honeycomb? What does being a developer advocate at Honeycomb actually mean?
So Honeycomb is a company that helps our clients achieve observability. And we do that by ingesting telemetry data from their systems, and we help process that and surface it so that people can get real-time insights into why is my site slow, which users are experiencing downtime, and help people correct that as quickly as possible. And As a developer advocate, my mission is to help make Honeycomb the best it can be for our developer audience. And that means everything from working in feature development to backend infrastructure to helping educate the world about what we're doing.
Right. Okay. That seems to cover a lot of bases. So if I'm using Honeycomb, I'm like sending telemetry from my web server and my database and from my blockchain or whatever, and letting you worry about showing it to me in a useful way, right?
Yes, that's precisely correct. That we have SDKs like OpenTelemetry that allow people to generate that telemetry data in the form of traces and trace bands and metrics, and they can send it all over to us, and then we handle reliably ingesting it and storing it and querying it.
Well, that's the question, isn't it? Reliably. Tell me a little bit about your architecture, because I know it's more than I would want to put together myself.
Yes, so there certainly are ways that you could, put together a first pass of a observability platform, right? That first pass might look like having like a Jaeger instance that is collecting the data and send it on to a Cassandra instance or something like that, right? Like that's one possible option, but at Honeycomb, we operate at a much larger scale than that would be feasible for. So we have a dedicated fleet of ingest workers that handle, making sure you're authorized to send this data. And then we slice and dice that data into individual events. And then we take each individual event and we send it off to Kafka for durable, reliable kind of serialization and ordering. And then on the other end of Kafka, we've got a fleet of consumers that are basically reading off the queue in order to break those events down into their constituent columns, right? So if you have a field that's called user agent, or a field that's called IP address, or a field that's called trace ID or span ID, each of those things from each event coming in order off the stream is appended to a file per attribute or per field. And that enables us to kind of group things together, right? That might share common properties, right? You might see common compression properties that you can use to kind of make the user agents compact down a lot. Or you might see that, you have almost every single value of, has cookies turned on is set to yes, right? Like those are things that you can do much more efficiently when you are dealing with all of the data from one column at one time.
What's the database there?
So our database here is a homegrown solution. It is a column store that is similar to Facebook's Scuba or the Google Dremel/Column.io backend.
Oh, yeah.
So basically, we are slicing and dicing the data, we're storing it and shipping it into flat files, and those flat files make their way over to S3 at some point. We invented this back in 2016, 2017. Like a lot of these technologies were not necessarily available open source, so we wound up building our own. Not necessarily that we'd make that decision today, but that's kind of the decision that we went with at the time in 2017.
Yeah. It's funny. Sometimes you make decisions that don't seem like they're that long away, but 5 years can be a very long time in internet time, right?
Oh, very much so. And especially in COVID time.
Yeah, absolutely. Yeah. I've been writing something myself, reflecting back on a business that we built, I think in 2012 it was. And in hindsight, we would have used Kafka, but I'm not sure Kafka was usable in 2012 in the way we would have needed it today, right?
Right, or people ask me today, well, doesn't Pulsar handle what you do? And I'm like, yes, I mean, maybe, but also we are in the world of having started this complex system in 2017 and maintaining the continuity of it at 99.99% reliability ever since.
There's the rub, right? That kind of reliability question. And you've grown
exactly,
a lot, right?
Yeah, we've grown a lot and our customer demands have increased, right? Like it doesn't suffice to drop customer data on the floor, right? Like our customers are relying upon us to get that telemetry data in, right? That's why they're paying us. So they don't have to worry about kind of where that telemetry gets sent. And we only, for the most part, we only get one chance to receive it. If we drop that batch of events, it's gone forever. There's a crater in that client's graph forever.
Yeah, absolutely. So as data's coming in, does it go straight into Kafka, or is there a step before Kafka?
We obviously have kind of these ingress controllers, right, that are handling, validation. Is your API key valid? Are you over quota? Kind of repacking things from whatever wire format we get, whether it be Z standard compressed JSON, gzip compressed JSON, or a gRPC protocol buffer, right? So we are validating these payloads, and then we are passing them on via a Kafka producer and using Z standard compression to kind of get the best bang for our buck and kind of serializing everything in a consistent format. The other interesting thing is there is one Kafka topic at Honeycomb. Right?
Really?
There is there's one producer and two consumers, right? Or two types of, one producer binary, two potential consumers, right? Like that's it. We are using Kafka at very high throughput, especially very high throughput per partition, but we're not actually using Kafka as a general purpose data bus. And I know that a lot of Confluent's other customers love using Kafka as a generic data bus, but that's not our particular use case, which I think is a definite case where we are different than a lot of the mainstream.
So it's really just one really wide topic, if that's it. How many partitions? Do you know, out of interest?
70.
70. That seems like a lot to me.
70.
Okay.
It's less than people recommend, right? Because people recommend that you have many, many partitions to let you kind of load balance between them pretty fluidly. But we've got only 70 partitions for a volume.
Okay. And what size of customer base is that serving?
Yes. So we are serving hundreds of enterprise customers. We are serving, essentially, we think in the observability world in terms of number of events per second, right? Like we think about number of trace spans that people are sending us per second. And this is actually something where I can use Honeycomb to introspect Honeycomb itself, right? Like I can go and look to see right now.
I was going to ask if you ate your own dog food on this.
Oh, yes, we do. So I can actually go in and look right now and see, how many messages per second is our Kafka processing. And the answer is our Kafka production cluster is processing about right now, it's as we tape this, 1.4 million messages per second.
1.4 million a second. That's real-time data in action. Love it. Crikey.
Yep.
Okay, but it was a journey to get there, right? So it took you a while to reach that kind of scale. So take me through some of the steps that actually got you to 1.4 million messages a second. Yeah,
so what happened was in 2019, we were a lot smaller of a company. We had only, 25 employees. We were serving, you could count the number of enterprise customers that we had on two hands, right? And that was a very different time because it meant that a lot of our cost was paid in terms of kind of ongoing overhead of infrastructure, right? That it was relatively, that you could scale out, but once you scaled out, you couldn't scale back in. So we were kind of, trying to write at the edge of what we could, knowing that if we ratchet it up, that was going to incur, like, now you can't ratchet back down, right? Like, you can't ratchet down the number of Kafka partitions. You can't, once, in our case, once you start sending data to a partition, once you have a consumer that's dedicated to reading from that partition, right? Like, scaling that back in doesn't quite work as well for us.
So, and you don't want the number of customers to decrease. Sorry, you don't want the number of customers to decrease, but it could happen, right?
Yeah, exactly. So kind of fixed costs and kind of quick and dirty scaling was kind of the way that we were approaching things, kind of to scale in these increments as we needed them. But also, this was a painful world in that, something like 1/10, like 1/5 or 1/10 of our company's burn rate was just our Amazon bill. So kind of that 10 to 20% mark was a little terrifying, especially as the costs kept on going up and up and up, the more data volume we went through.
Was it linear? Was the price going up roughly with a number of customers, or was it worse than that?
Yeah, it was going up with a number of customers, but also there was kind of this tension of, we know that even if we are getting more revenue per customer, like having that burn rate go up linearly at the same time, that's a little terrifying when you're a startup and your runway is measured in months.
Yeah, that's true. So give me some technical details. What did you do to start solving that? What's the first step?
So the first thing that we knew that we needed to do was we knew that we needed to stop paying Amazon for redundancy that we already had inside of our Kafka cluster. It was either, we stay on EBS volumes, C5 instances, and that we just go to a replication factor of 2 rather than 3. That was kind of the first cost-cutting measure we talked about.
Right.
But we had some chats, right? Like, and we were like, hey, Amazon, we're considering going from 3 to 2. Like, there is a cost that if this blows up in our faces, like, we're going to get mad at you. And they were like, no, don't do that. Like, stay at replication factor 3. Like, we'd rather work with you to figure out, like, what's needed to make that possible, right? So, seeing that, basically, we evaluated everything from, how much data are we transmitting across availability zone boundaries, right? Like, ideally, you should only be transmitting across one time, right? Like, per replication, you shouldn't be, reading from multiple different availability zones. That was kind of one recommendation they gave us. But then the other interesting thing was we realized that Elastic Block Store is, there is no commitment discount to EBS. That if you have a Kafka volume that is, 1 terabyte, like, you are going to be paying, that's what, 10 cents per gigabyte. That's like $100 per month per terabyte, right?
Right. So there's only a discount for processing, not for storage.
Yeah, there's only a discount on buying whole instances. And I don't even think AWS S3 has a volume discount, at least not listed on the website, right? So it was this challenge of, okay, like, if we know that we are already having a replication factor of 3, mm-hmm. and they're scattered across different availability zones, do we really need to be paying Amazon for the ability to attach and detach volumes from instances or to survive the loss of an individual instance, right? Like, EBS has its own redundancy mechanisms.
Yeah.
So what we realized was we could get cheaper storage and get the compute essentially for free. If we switched from running C5 instances and EBS to doing a reserved instance purchase of I3 of I3 EN instances, right? Like the kind of high storage local SSD instances where if you terminate the instance, you lose local storage, right? But that you can make a commitment, right? Like there is a volume pricing, a commitment pricing to it that if you say, I'm going to need, 6 I3 EN instances for the next 12 months, they'll give you a discounted rate, which is actually, I think, 20% lower than just the cost of the EBS volume that you would have needed for the equivalent amount of SSD. Yeah.
If you can do your own recovery situation, then you've got...
Yeah, which Kafka provides for.
It's cheaper to have processing and temporary storage than just the storage.
Yes.
Okay, that must have been a happy realization.
That was a very happy realization that we had for sure, was that there was a way to kind of limit and constrain the cost. The downside of that means that, you now lose the flexibility with an EBS volume. You can say, hey, I need more storage, increase the storage, right? Like, let's ratchet up the storage meter, right? And it'll just let you extend the file system. Everything's fine, right? Like, in this case, if you need more storage, you need more brokers, right? And then the flip side to this was actually this interesting waste, right? Like, we were buying, 20, 30 of these instances, and we were barely touching the CPU on them, right? Like, we were just using them for the local disk.
Right, yeah. So did you find a way to use it, or is it just sitting there idle now?
Nope. We just let it sit there idle, right? Like,
God.
we were very, very, paranoid, right? Like that if you just loaded up your Kafka cluster with a unrelated workload, it would hurt your latency and thereby impact reliability for users, right? If someone sends us a payload of data, they expect that data to get ingested within 5 milliseconds per event that they send us, right? Mm-hmm. Otherwise, it starts buffering in RAM on their hosts rather than getting shipped off to us. So we knew we wanted to keep that very, very low latency. So yeah, that was kind of the first step that we took, was like, hey, like, let's pay less for the storage.
But do you have a problem if they suddenly go down, that you lose data, or is there a recovery story there?
Yes. So this is part of what we continuously test at Honeycomb. We continuously test our assumptions about recovery. Mm-hmm. So for instance, we talked about the consumers, right? The retriever processes that kind of tail off of Kafka and serialize things into column stores. Right, so we kill one of those processes every week, right? Like, we completely delete the instance and test our automation to make sure it provisions the new one, that's able to bootstrap, that's able to replicate data and start, catching up based off of where it was in Kafka. Mm-hmm. So we started doing the same thing to our Kafka instances, right? Like, we would kill one per week and verify that our mechanisms for re-replicating under-replicated partitions, right, and kind of replacing the old broker with the new broker. We started getting into a cadence of regular broker replacements just to validate that if Amazon, makes one of our instances go away, then it's not going to be an emergency.
Okay, so you've got recoverability sorted. You've got this cheaper workaround for storage. Can I call it a workaround?
Yeah, you can call it a workaround.
What's the next step to reaching your present-day scale?
Yeah, so I think the next step that we took here was, at this point, I mentioned Z-Standard earlier in this conversation. So we were starting to use Z-Standard to transmit from our clients to us in some cases, but we were still using Snappy
compression protocol, right?
Yeah, that's the compression protocol.
Yeah.
So we were using Snappy from the Kafka producer to the broker to the consumer, but that was primarily because we knew we wanted to use Z-Standard, but our client library, because we were a Go shop, we are not quite as happy to use a C++ Kafka client like the, I know Confluent has put a lot of effort into the C++ client, high performance client, but we use the Surama native Go client. So it took a while for the Surama native Go client to have Z-Standard support. So once they had it, we adopted Z-Standard, and basically that instantly cut 25% of the bytes that we were storing on disk, 25% of our bandwidth. It was this massive, massive win to be able to send the same amount of uncompressed data through, but to have it become compressed to be 25% less than it was before.
Was that just because it was a native form? I mean, why do you think it made such a difference? Is it a better suited algorithm?
For our particular workload, for our particular workload, it just delivered much better compression. We had many repeated strings and other kinds of things that the compression algorithm was able to deal with more effectively.
Right, okay. Yeah, that makes a lot of sense. Repeated strings are ripe for the right kind of algorithm to be chewed through, right?
Yeah, exactly. Definitely makes it a lot easier, right? Like, if you get the batching right? Like, you can't compress 10 messages at a time. You might have to compress 100 messages at a time, but like, eventually you find those redundancies that are coming through.
Right, yeah, and they're worth finding at your kind of scale.
Yeah.
Okay.
But the kind of the challenge that, eventually we hit was that, even when you compress, right? Like, you are still, right, like in this circumstance, you're running on a fixed number of brokers, right? Like, or you have like a relatively finite number of brokers. Each disk on that broker has a finite amount of space. And we are seeing that kind of margin of what we could keep without filling the disks on our brokers, right? Like, because we were doing bytes-based retention policies, we found that started to erode, that we previously were able to keep 36 hours, 48 hours of data around. But it suddenly got to be less than 24 hours, and we were like, uh-oh, this is a problem. Like, this is not good.
Yeah, you can easily have a problem that lasts longer than 24 hours if you're having a bad day, right? That's all it takes.
Right, like it's not that it impacts our day-to-day operations, right? Like under normal circumstances, we're only like replaying the last hour of data, 2 hours of data at most. But if something goes really, really wrong, right? Like let's suppose we have a data-eating bug in our storage engine. We need to be able to go back and replay that older data, right? To be able to reconstruct it. And if there's not enough of that window left around, because we discover a bug on Saturday morning, and we realize that this has been a problem since Thursday or Friday, right? Like, and let's suppose it takes us until Sunday to like find the bug, fix the bug, right? Like you have to have that 48 to 72 hours of replay buffer, or else like you have the possibility that you don't have a backup plan, you don't have a recovery plan. So for us, Kafka was our recovery plan, but as we're talking about, right, like we only read the most recent hour or two of data under normal circumstances. So it's like, this is interesting. This is almost the worst of all worlds, right? Like where we are paying to store on very, very hot local storage 20 hours of data, right? Which is the wrong amount of data for long-term recovery, and it's the wrong amount of data for our daily operational needs. It's terrible, right?
Right, yeah, I see. So why are you not just reconstructing entirely from Kafka? That feels like the first strategy I'd go with. Every time you need to recover.
Sorry, I'm not sure that I follow that.
Sorry,
the goal was to be... The goal was to be able to recover from Kafka, right? Like to recover data from Kafka up to 48 hours old, right? Again, we recognize that Kafka is a streaming solution, but at the same time, we don't necessarily want to use something like KSQL because we're hoping to look at 60 days of data, right? Like that's kind of why we digest the data into the column store, why we export it off to S3, right? The question is if you have questions about the quality of that data that's on your local disk or on your S3, right, then you have to go back in time and you have to replay Kafka forwards. But if the data is not there in Kafka, you can't reconstruct the data forwards. That was kind of the central problem.
Right. So how? I mean, I can't quite see how you then squared that circle. What do? You've got this exactly wrong amount of recovery window. Where did you go?
Yeah, we got the wrong amount of recovery
buffer
buffer that we're overpaying, right? Yeah, so we looked at what it would have taken to kind of increase the capacity, and that turns out to be, as we were talking about at the start of this, right, like the linear scaling cost, right? That you are paying for more instances, for more storage, and that just didn't add up. That didn't make sense for us, especially given that we knew that under normal circumstances we wouldn't be reading from this. It was an insurance policy, and that is an awfully expensive insurance policy that's costing you, hundreds of thousands or millions of dollars per year. That's not worth it. So what we settled upon was we actually had seen blog posts from Confluent saying that you all were working on a solution to this problem. What happens if you have data that you need to retain for a longer period of time for archival purposes, but that you don't necessarily need fast access to it. So this was the Confluent tiered storage feature that appeared in Confluent Platform 6.0. So we started inquiring about it because this seemed like a thing where we had been long-time Confluent Community Edition users, but this was kind of the first thing that kind of really made us think about whether we would see value out of paying for Confluent Platform.
Right, yeah. The idea
because we'd done these experiments before, right? Like we'd done these experiments of hey, what happens if you, store a portion of your data on a EBS, cold hard drive storage platters, right? Like EBS offers you the option of getting cold hard disk platters, but we tried it and it didn't really work for us because, we were rolling our own tiered storage essentially. rolling
Right.
our own tiered storage, basically saying like, hey, LVM, you are the storage system. Go sort out which blocks are hot and which blocks are cold, right? Like, except for it has no knowledge of the file system, no knowledge of which files are hot, no knowledge of like, this file this file is useless unless you have all of the blocks, right? Like, it didn't know or understand any of that, so it did a really terrible job.
It's got to understand your data model and your file system structure to actually do it properly, right?
Yeah, exactly. So we were seeing, produce times that were in the, hundreds of milliseconds at the 99th percentile, and that was not acceptable to us. So we had to back out of that. So we tried it before. We knew it was a challenging problem. Right. And we knew that the right people to solve this were going to be people who are experts in Kafka, who understood how to tell the Kafka broker, this is how you request cold data. This is how, this is what to do with the data once it's sitting there.
Yeah, I can absolutely see that's only going to work if it's a Kafka level concern, right? So how did it go?
So we started doing a proof of concept of this in, trying to think about this. That would have been the end of 2020. We started doing the proof of concept of trying out tiered storage, seeing whether it would work for us, kind of initially kicking the tires with, we mentioned earlier the dog fooding, right? So we have a dog food environment, and it's a 1/3 or like roughly 1/3, 1/4 model scale of our production deployment. And that allowed us to gain some confidence in it that, it would tolerate broker death, that it would tolerate, what the latencies were like if you fetch that historical data. And then we went into production in January of this year, of 2021. And we started deploying it out at scale.
Right. It occurs to me that your scale model, if it's a quarter, must be a mere 350,000 messages a second, right?
Yep,
Just
something like that.
Tiny little model.
Nearly, yeah.
Oh, crikey.
Right,
okay.
like it has this really cool property of, it is a really, right, like it's not a fake staging environment. It's something that Honeycomb employees, we use it every day. And
but you've proved that already, right?
Many of the aspects of our system. Yeah.
Yeah, okay, I'm convinced. You've given me a demo already. Okay, so you roll out Confluent platform tiered storage. How did it go?
Yeah. It wasn't Confluent's fault, but it exploded in our face. And what happened was we tried to change too many variables at the same time. We were trying to do both tiered storage at the same time, and we were trying a new class of Amazon instances that had a brand new Nitro hardware and kind of firmware supervisor. And we also in the course of this, we also were trying to go back onto EBS, right? Like, because we were like, you know what? Like, actually, we value the ability to twist that knob. Like, we're only going to size the EBS appropriately for 2 or 3 hours of data. But like, let's try, new instances, new tiered storage, new firmware. Right? Like, this is the newest generation of everything. Let's do it all at once, right? Like,
so an ambitious start to the year. And
let's just start to the year that ended in way too much pain.
Okay.
So yeah, and
that
in
feels
the
like
course
a timely
of that,
warning.
It was a timely warning. We also had made some suboptimal decisions around. I think we had an earlier conversation about, is it safe to turn on is it safe to turn on nclean leader elections? So we turned on briefly nclean leader elections, and it had accidentally gotten set on the tiering topic, because Kafka, right, like all of Confluent's features utilize, and again, dog fooding, right, like all of Confluent's features use Kafka as the data store. So it turns out when you have nclean leader elections on your tiering topic, that will cause the tiering system to go, oh God, something bad has happened, right? Like I'm going to fail safe by not tiering. So all of our disks started filling up, right? Like on top of all this chaos. It was,
God.
Yeah, it was, it was a little painful. So we had to kind of reset and be like, okay, let's, set back to a bunch of conservative settings, right? Like we're going to go back to the, regular kind of, instance store instances. We can get slightly larger instance store instances, and it still is a cost savings because we're running fewer of them, right? Like we're only running 6 and not, 30 of these things. right?
Okay.
And, saying like, hey, like, okay, unclean leader elections, bad idea. Don't do it, right? Right? Why do we even, in the Emperor's New Groove, right? Like, why do we even have that lever?
Yeah.
So kind of all of these things where we're like, okay, back to basics. Like, let's just deploy tiered storage by itself, and it worked phenomenally. It was fine.
Oh, cool.
And it kind of basically did exactly what it expected on the tin when it was the only variable you changed at a time. And then after that, we were kind of able to iterate from there and kind of make smaller changes.
One step at a time.
Yeah, one step at a time.
Much more smooth.
So then I think that brings us to the kind of last improvement that we made, which was about a month and a half ago, really. About a month and a half ago, Amazon contacted us and said, like, hey, we hear that you like our instance store bulk storage, like i3 EN series. We hear you like Graviton 2, which is the ARM-based instances that are lower total cost of ownership. Are you interested in trying this combination of storage instances that are based on ARM? And we said yes, right? Like that seemed like a useful thing to try.
Still hungry for the bleeding edge.
It was... right, like with plans to potentially be able to fall back, right? Like, and also changing only one thing at a time, right? That's what we had gotten wrong the first time around, was that we change everything at a time. Now we had tiered storage running stably. Now we could actually go and say, okay, like now we're going to change the underlying instance type on a stable, non-changing set of software.
Right. Yeah. Okay, that makes sense.
So we did some initial validation, and Amazon, was very clear with us, hey, like, you're not allowed to use this production workload until like we give the all clear, which is fine. But like, we also, having been burned from last year, having burned by, this, the scale model worked fine in dog food at 1/3 scale. We deployed the to two of our production, 2 out of our 6 production Kafka brokers, this new architecture, just to make sure it would hold up under load, right?
Right.
Because we knew that the load properties were subtly different between dog food and production, right? Like, this wasn't us utilizing it cheekily for production load. This was us doing this as part of our validation process to be able to confidently say, we think once this goes GA, we're actually going to be able to switch over. We don't want a repeat of January where we tried a thing and it didn't work.
Yeah, absolutely. So how long did it take for that to roll out? For you to bed it in and decide to put it in production?
So that's kind of, I think, yeah. It basically took us 2.5 weeks to be confident enough. So we rolled most of our dog food cluster. We rolled a third of our production cluster, and then we had enough confidence based on the performance data that we're seeing that the claims that Amazon had that it would be just as much storage, and that it would be and it would give us twice the CPU, and it would only cost like 14% more than the previous instances we were using. Oh, and double the network too, right? Like that had all these properties that would let us scale up without increasing the cost any further than just paying 14% more for the instances. And get double the performance out of it. We were like, okay, yeah, sold. Like that seems good.
Yeah.
So they announced it at reInvent on, I think, November 30th or December 1st. And by the end of that week, we were 100% migrated over. Kind of a combination of us testing our recovery processes by killing brokers every week anyway. So we knew that the kind of broker replacement worked well. So we just, rotated through all the instances and, kill one, kill the next one, right? Like wait for them to replicate and then just keep proceeding. So it took us less than a week to fully cut over our entire workload to the new instances.
Okay. And how's it been going since then?
Buttery smooth. Completely buttery smooth. Now the last things that we're kind of trying to work on are just further decreasing that cross availability zone reading process. So, trying to read from local Kafka brokers when we can. And otherwise, just kind of keeping an eye on the system using the Honeycomb metrics product to look at the Kafka broker metrics. And, Kafka is no longer a scaling pain that we have anymore. Basically right now, I'm looking at this dashboard and it's like, it's the peak of the day on Monday, and we're at 30% saturation on CPU on our brokers. We're at roughly 30% saturation on disk on the brokers, right? Like this feels like a system that can comfortably scale by another factor of 2 and be all right. So it's kind of one of those things where you think about this way that the system was 2 years ago, and you're like, oh gosh, this would have been like scary, right? Like we'd be juggling Kafka brokers. We'd be, paying for all of these C5 brokers with all of their EBS drives. Like this would have been like, and we had like very little automation around broker replacements. And now it's basically running itself, healing itself, and kind of just, not automatically scaling, but, we know what the capacity dimensions are, having hit many of them over the past year. Like we know what we need to do to keep this thing running.
Yeah. Yeah. And it makes you think, doesn't it, that things like metrics at first glance seems like such an easy thing to just be an afterthought in a system. But when you really start to get up to serious scale, there are so many small levers to pull and bits to check and test to get actual kind of scalable performance you need, right?
Right, exactly. We think about this, and the headline number on our case study is something like 87% reduction cost per megabyte, right? Like, and that didn't come from any one specific change, right? Like it's just a series of anywhere between 25 to 40% savings at each with each adjustment that we made.
Yeah. Crikey.
So you kind of have to chain these improvements together, and then and that's how you kind of keep that cost low and the overhead low.
Yeah. Well, it's one of those things that's kind of fascinating, but I'm glad I didn't have to do it.
Yeah, and this is the thing that we repeatedly try to emphasize to people is like, if you want any kind of reliability of your observability pipeline, you're going to want to have Kafka in there or Pulsar or something like it, right? Except for we know that Pulsar is less mature because it's less battle tested, right? So, okay, you're going to need a streaming data solution to ingest your streaming observability data.
Yeah.
Now, do you really think that you can do a great job of running that, right? Like, versus someone who is paid to work, mostly full time on it, right? Like, and even in our case, right, like we are decent, we think these days at operating Kafka, but we still very much rely on and appreciate being able to turn to Confluent for kind of any help with the actual like Kafka code itself, right? Like, So it's one of these situations where unless you're very, very good at operating this particular kind of Kafka that is very, very high throughput per topic, right? Like, you're probably not going to do a better job of running your own observability pipeline as opposed to trusting someone who does it as their professional job. Oh, and by the way, where we also have a design team that thinks about how do you design a good user experience when interacting with this data, or how do you handle the fast querying of the data, because it's not just the streaming reliability, it's also the how you surface it quickly for querying, right? Like there's so many dimensions that go into potentially building your own, like that. We think that a lot of what we're sharing here as lessons are not so much things that, it's not so much a thing of you should build your own. It's if you are using Kafka, here's how to optimize the cost, but think about whether you really want to be running your own Kafka. And, this is why we're glad that Confluent Cloud exists, right? Like that if people, need a slightly smaller scale Kafka and they want a metered access, like that's available to them. They don't have to kind of stand up their own brokers.
Yeah, yeah. Plus, on top of all that, it makes me think, like, if you're these metrics, the very day you need them to be working well is your bad day, right? If there's a disaster in your business, a disaster in your system,
and of course
that's the day you need this other thing to be completely reliable. There are always correlated
failures, right? Like, there are always correlated failures, right? Like if US East 1 goes down, everyone's having a bad time. We didn't go out, but there was a lot of scrambling during that week in which everyone else was having significantly worse pain. But yeah, it can happen. But definitely, if you are having an outage in your own infrastructure only, right, like, you don't want a correlated failure of your observability.
Yeah. God. Well, thank you, Liz, and thank you, Honeycomb, for putting in all that work so that I never have to.
Yeah, of course. It's it's what keeps me coming to work every day is making developers' lives easier with better observability.
Cool. Well, It's been a pleasure observing your story. Can I get away with that pun? I'm going to try to. And terrible pun. Yes, thank you for joining us on the show. I know you have a blog post if anyone wants more gory details on this story, and we'll put that in the show notes. In the meantime, Liz Fong-Jones of Honeycomb, thank you very much for joining us.
Thanks for having me on the show.
And that wraps it up for another episode of Streaming Audio. Before we go, let me remind you that we're brought to you by developer.confluent.io, the website that will teach you everything we know about Kafka, how to scale it, how to make it perform, and how to get started. Because that's important too. You can't scale it until you've got started, can you? So why don't you join us on one of our courses that will teach you everything you need to know? And if you do use one of our courses and sign up to Confluent Cloud, use the code podcast100 and we'll give you $100 of extra free credit. In the meantime, let me say thank you once again to our guest this week, Liz Fong-Jones. Thank you to Honeycomb for sending her to us. And thank you for listening. If you have any comments or questions, or you just want to get in touch, you can find us on all the usual internet channels. If you're watching this on YouTube, there's probably a box just down there. And if you're listening to the podcast on audio only, have a look in the show notes because we include all our contact details there. Thank you very much for joining us. Until next time.